Hey guys, so first of all, Happy New Year, Happy 2025. For those of you who don't know me, my name is Oscar Sabalainen. I do a lot of AI stuff, particularly a lot of neural network quantization stuff. And today, I actually will not be talking just about neural network quantization. I'm going to be talking about something that I've been working on the side and that me and my friend have just open sourced and released, and we're quite excited about it. And it seems to be doing well as well. We released it a few weeks ago and it already has 10,000 downloads, so woo! Happy days. It's something me and my friend Saf, who is just a ML ops wizard. Like, the man is a complete beast when it comes to like ML ops. It's intimidating. But yeah, close friend of mine, and he and I have been working on this for about 6 months now. So yeah, here to talk about Alma, which is our open source Python package for basically benchmarking your model speed on all of these kind of different PyTorch conversion options. So hopefully this will be relevant and or interesting to you. And with all that said, yeah, let's just get into Alma. So yeah, this is Alma. It's on Saf's GitHub and it looks like this. So as I said, it's a Python library for benchmarking your model speed across different conversion options. And the idea is that, okay, you have your model, but how should you run it in Inference? There's an eye-watering number of options. And the idea of Alma is to package those all together in kind of an easy-to-use way. And then it lets people experiment with it. So, for example, JIT tracing, Torch compile, Torch export, Torch AO, Onyx, OpenVINO, TensorRT, half precision options. We have a bunch and different combinations of them. And the idea is that with one function call, you can get a full report on how fast your model is for whatever data that you provide across all of these options or just a subset of these options, however you wish. So using it is really easy. You can just pip install it, or you can clone the repo and install it locally. We recommend that you work within the Docker container just because a lot of these options have dependencies and they might conflict with each other. Using the Docker image is going to ensure that everything works in case you have any issues. It's easier to work within the Docker image, and all credit where credit is due. Like I said, Saf is an ML ops wizard. He built this entire thing to get all of the dependencies running, which was not easy. But this is what it looks like in code. So first of all, we import a bunch of stuff from Alma. We initialize our model. We initialize a data loader if we want to. Later on, when I talk more about like advanced use cases of Alma, I'll talk about how you don't necessarily need a data loader, you could just use a data tensor. But for this example, you initialize a data loader. We create a config, which is just our benchmarking config, and that's just going to tell us how do we want to do this benchmarking? What's the total number of samples that we want to benchmark across? What should the batch size be? What device should we run on? Then we feed in our different conversion options. So in this case, eager is just vanilla PyTorch. It's you take your PyTorch model, you put it in eval mode, you run it with torch no grad. That's going to be this eager speed. That's like vanilla PyTorch with no modifications. Torch script. If you are familiar with the PyTorch ecosystem, you might be aware of Torch script. It's the OG precursor along with JIT tracing to Torch 2.0. And Torch script does not work for every model. If you have data dependent control flows or anything that's not immediately traceable in a graph, Torch script will not work, versus Torch 2.0 with like Torch compile that will work, which is why, Torch 2.0 exists in the first place. But it's an interesting option to mess around with. Then Torch compile with the inductor backend, which is like PyTorch's default backend for Torch compile. And that comes with different options. You have reduce overhead, you have default, max autotune is the most aggressive option, and then Torch compile, but using the OpenXLA backend, which I think it's open source, but I think it's supported by Google. I think the main developers are Google developers. And yeah, so we're just going to run these 4 options in the example. You just run it into benchmark model, you pass your model, you pass your conversions, you pass your config, and then that returns a dict of results, and then we can display all of the results with another function call, or you can display it however you wish. But the results, depending on your hardware, might look like this. This was run on a Titan NVIDIA GPU, and we see that for eager, just shy of 300k samples per second. For Torch script, just shy of 500,000, which is already a pretty big improvement, but we can do better. With Torch compile with the inductor, we get just shy of 600,000. And I found it pretty impressive that the OpenXLA backend for a PyTorch model actually beat the most aggressive Torch Inductor Max Autotune option, which is pretty cool. So like OpenXLA seems to be very interesting in terms of optimizing for speed. We have a lot of documentation in our examples about advanced use cases, because you can have a multiprocessing setup to ensure that each process is run in kind of a self-contained child process to avoid contaminating the torch state. We have the optional graceful failures, device fallbacks. There's a bunch of like interesting stuff that we discuss in the documentation, and I'll talk about that in the second half of the video, but the first half is just like a general overview. In terms of all of the different options that we support, there is, I think, quite a lot. Here there is 48, and they include everything from eager, export, Onyx options, Torch compile options, export with quantization, export with compile, native quantization options, which is just for like edge devices, doesn't really run on GPU. We have JIT tracing, Torch Cryptum, Optimum Quanto, which is a Hugging Face quantization library. We have half precision options, and I'm going to be adding way more to this just after I film this video. And then some Torch AO options as well, which is like PyTorch's native GPU quantization. So we have a lot of different options. It's very easy to add more options. In terms of future work, we're always looking to add more options, and it's made to be done in a way that's really easy and easily scalable. Running across multiple devices as well would be really cool. Like currently the model has to exist on one device, but it would be cool if you could split the model across multiple devices and then benchmark the speed of that. That would be really cool. And then integrating options similar as above, but beyond PyTorch. Like Hugging Face, we already have a few options from there, but things like JAX would be also really cool. Maybe some LLM specific stuff like Llama CPP or VLLM. So yeah, that's Alma in a nutshell. Obviously contributions are welcome. It's an open source repo, anyone can contribute. We released this, I think like 2 weeks ago, and already people have been like opening up issues. We've already closed a few of these issues, but it's been really cool. It's been a fun experience, but you know, if you want to contribute, we'd be happy to have you. And yeah, that's it for the broad overview of Alma. It's a Python library for benchmarking your model speed across all of these different conversion options. And you can, if you don't feed in a list of conversion options, it'll benchmark across all of the supported ones. I think it's a really fun project and it's been really fun to work on. For those of you who are interested, I'm now going to dive into a bit more of the documentation. If you want to jump off, totally cool. I won't begrudge you. But for those of you who are interested, I'm going to go through the documentation. We have two major examples. We have MNIST, which is our most complete option by far. So this has a lot of documentation. It's just a small computer vision model and will show you can train it, you can quantize it, etc. But it has a lot of documentation around Alma. Then we have a small linear model, which is literally just a linear layer with a ReLU. That's all it is. It also has some example scripts. We also provide a Jupyter notebook for that because some people really like those, and it talks through more and more advanced use cases of Alma. For now, I'm going to look at the MNIST just because this is like the most complete README and a lot of the documentation lives here. But before I do that, I'll say that there's these 3 different scripts in this MNIST example. There's benchmark with random tensor, which instead of the thing I mentioned earlier about you don't need a data loader, you can just initialize a data tensor and just use that. And if you do so, we will internally initialize a data loader, and so you don't have to go through the bother of initializing a data loader. We'll do it for you. All you have to do is create a data tensor or whatever shape that you want, and you feed it in. You feed it in without a batch dimension. This is why I have the squeeze here, and the size of 1 for the batch that gets squeezed away because the batch size gets controlled via the benchmarking config, just something to be aware of. But yeah, you can just feed in a data tensor, and then internally we will create a data loader that will produce random tensors of the same shape as this, and then use that in benchmarking. Then we have this other example with a data loader that you can use. We initialize a data loader that will work with this model. All of these will just run. And then we also have a memory efficient benchmarking thing, which I will discuss a little bit later because it has to do with the multiprocessing, which we have not gone over yet. Cool. So yeah, if we start diving into this is, I mean, basically what I showed earlier. There's not really any difference. It's your kind of standard data loader, your config, you can run it, and these are the kind of results that you might get, and the instructions on if you want to run the entire example. We do provide an argument parser if you want to use it via the command line. That's totally cool. So we give a bunch of options here, typical ones being like, okay, you can feed in your model weight if you want to, you can pick whichever conversion options you want, you can pick this as a string with the name of the conversion option, or as an integer using its index, or a mix of the both. Those are both available. You can control the batch size, the number of samples, the data that you want to benchmark on, as long as some other options, and you can see all of the options while running help. And like I mentioned, you can have a combination of strings and integers, but that's for people who really want to use it via the CLI. Then we don't need to use an explicit data loader. We can initialize a data loader internally. So that's what this kind of example goes over. Graceful or fast failures. By default, Alma will fail gracefully in case some option doesn't work on your hardware. For example, not every option supports every piece of hardware out there. There's cutting edge stuff. But on top of that, some of the models that you can create in PyTorch won't support certain conversion options, like Torch script. It doesn't support the entire set of PyTorch models. So if that is the case, if something does fail, you can set your fail on error to false, which is the default, but if you set it to true, as soon as it comes across a conversion method that doesn't work, it will just crash, and you can see why it crashed. But in this case, if I'm running this on Mac, the native fake quantized kernels don't work. And they don't work just because the kernel hasn't been written for MPS, which is, what Mac Silicon runs on. And the only way to get it to work is that you have to run it with this environmental flag. But if you don't, this is what you might end up with. We can see that the eager result, came back positive, but then this just returns the error. You can customize what you want this to look like. You can have no error message. You can have an error message. You can have the error with the traceback, or you can access all of it in your own time via the returned results. So in this case, results fake quantized, traceback is going to give us something like this, where we can see that, okay, yeah, it goes all the way down to when it calls the kernel, and then it's going to fail. So I particularly think this is really cool. We got it working with multiprocessing, which was non-trivial to do. But yeah, it's fun. So you can just see what went wrong and you can debug your stuff. I've mentioned multiprocessing a few times. The reason we use multiprocessing is because we needed a way to run each conversion option inside an isolated environment, and this is needed because some of these options actually affect the kind of global torch state. If I take Optimum Quanto as an example of this, which is Hugging Face's quantization libraries, it's intended to have high-level APIs that make quantization really easy, and it does so very well. But Optimum Quanto has some issues with it, and it comes down to design choices, really. So the way that Optimum Quanto works, the way they're able to have these really high-level APIs, like quantize, which turns things to fake quant, and then freeze, which kind of converts these weight tensors to actual, compressed quantized weight tensors. The reason they're able to use these high-level APIs is because they actually rewrite some stuff in the Torch backend, particularly a lot of the C++ stuff, which unfortunately breaks a lot of the other conversion options. So if you run an Optimum Quanto option and then something else, it won't run the other option correctly. And so we thought about different ways of dealing with this. We were like, okay, we could try to reset the torch state in some way. That's tricky. Different options might reset it in different ways. It's difficult to know if you called every single thing that has been changed in the torch global state. And so what we opted to do instead is that every method by default gets run in its own kind of child process. So we use multiprocessing. So we spin up a new Python instance, we benchmark the model on whatever conversion option, then we close that process, we open up a new child process, and we benchmark the new method. And we do that for every single kind of conversion option sequentially. You can turn that off, particularly if you're trying to debug something. It can be useful to turn multiprocessing off, but by default it is on. This does have consequences on model memory, because you can imagine a situation where you initialize your model on the parent process and then it gets copied over to the child process, and so you end up having this process live in two different places in memory. Your model lives in two different places, which is not very efficient. You can, instead of initializing the model in the parent process, return a callable, pass that callable forward, and then only initialize it in the child process, basically. And that's what the memory efficient example shows how to do. And if you don't do that, it's okay. We'll just log a warning. We'll let you know that something has gone wrong. Then different things like you don't have to use this benchmark config, you can just pass in a dict, and then, internally it will wrap it with this benchmark config, which is a Pydantic data class, which is really useful, really like Pydantic. Device fallbacks, this is just options about if you run a conversion method, let's say you're running on GPU and it doesn't support GPU, it only runs on CPU, then you can gracefully fall back to some other option, and you can control how you do that by allowing device overrides. Do you allow CUDA fallbacks? Do you allow MPS fallbacks? So they're just useful. For example, like Onyx CPU will fail on GPU. The kind of native conversion option that I talked about on CPU, that's not going to work on GPU. Can you fall back to CPU, etc. So you have those options available as well, depending on how you want this to all be used. And then a bunch of logging and CI integration stuff. So we have the ability to save the results, the dict to JSON, which is really convenient for a lot of like continuous integrations. In terms of logging, I can actually show this to you in code. So if I run this example, it's going to benchmark all of these different conversion options. And really all that I want to show now is that as we are benchmarking these different options, right? Let's say we're running whatever, we're trying the eager method there, and then that kind of goes successfully. Then we do export plus eager, then we do Onyx CPU. What we see is that this is not a lot seems to be happening in the logs, but internally, a lot of these options are really verbose. Compile CUDA graphs, very verbose. Torch compile generally like spits out a lot of like internal log. And so what we did is we opted to just suppress all of those logs. So we told the model to basically shut up, don't do any of this. If you want access to those internal logs, set your debugging level to debug, and then that will release all of the different options. So if I go to an example, here we set the debugging level to info, but if you set it to debug, then you can get all of those internal logs as well. So that's it really, as far as all the examples go. I will show one last couple of things, which is how you can add new options, because I think and basically what's happening under the hood. How do we select all of these different options? So it's basically just a glorified match case statement. Like we've made it, which in turn is just a glorified if statement. And really what it does is that it just checks, okay, we want to run this option. Okay, what do? We're going to get the forward call for that conversion option. So really what it takes in the model, maybe some sample data, and then maybe some extra options, and then it will create that conversion option, and then it will return the forward call. So a good example of this would be, probably the simplest example that we have is JIT tracing, which is really simple. You just literally get the JIT trace the model, you need to feed some data through it, you run it in eval, and then you return the forward call. It's that simple. It's still very simple, but slightly more advanced. There's like floating point 16. You can cast the model to half precision, which is floating point 16. Then you can cast the data as you feed it through. And we do this in this kind of wrapped way, and then you return the forward call. So if you ever want to add a new option, it is exceedingly simple to do. Like I said, I think we have 48 different options that kind of split up across these different files. But yeah, that is Alma in a nutshell. Like I said, Saf and I have been, it was fairly chill for like 6 months or something. We were working on it on and off, but then in the last month we put a heavy amount of work into this to get it productionized and ready. And yeah, we hope it's useful to you and or interesting. We're going to be adding more and more options as we go. I'm not going to be surprised, probably soon, really soon. I think we'll probably be north of 60 or even 70 different options. It's been a fantastic learning experience. And yeah, hopefully it's useful to the open source community. So that is it for Alma. Okay, yeah, that is Alma in a nutshell. As you can imagine, it was a decent amount of work to get that done. As always, if you have any questions or anything, feel free to reach out. For Alma specifically, the best place to do that is via the issues. If you want a different method to be supported, just open up an issue. Some people have done that already. If you want to contribute, open up a PR. It would be massively appreciated. We also have a Discord channel that you can feel free to join. If it's for anything else, you can leave a comment on this YouTube channel. You can reach out to me on LinkedIn. People do that a fair amount, which I always appreciate it. And that is it, really. I will say I'm going to be releasing a few videos coming up about some quantization stuff, because I spent the winter break reading a ton of quantization papers and I have a lot more to read. I also been learning a decent amount of GPU programming. I'm working my way through the textbook. So there's a lot of really cool stuff coming out of that, and I want let people know what the kind of state of quantization and stuff is. So that'll be hot on the heels of this video. I'll make another one. And overall, yeah, I think 2025 is going to be like a really cool year in terms of machine learning. I think a lot of really cool techniques are going to come out. People are making interesting stuff. As we're running into the limits of LLM, scaling laws, and pre-training, I think that's going to open up the door to a lot of really smart stuff, because there's something a little bit dumb about just make the model bigger, give it more data. But I think now it's, people worry about like we're running into the limits of that, but I think we are like, actually it's going to open up the door to a lot more like innovation and stuff, because suddenly we're not able to pick the low-hanging fruit anymore. We're going to have to do more advanced stuff. So I'm actually really excited about that. I think a lot of cool stuff is going to come out. And yeah, I hope it's a good year for everyone, and I hope 2024 was a good year for anyone. And yeah, see you in the next video. Ciao.